Alright, hello everybody, and today we're going to be having a look at how exactly we can define a matrix raised to another matrix. Because we know how to raise a matrix to some power, let's say 3, and we know how to raise a number, let's say e, to a matrix m. But we don't really know how to define a matrix raised to another matrix, let's say m raised to some power n. And that's what we want to have a look at in this video. And I'll actually do a full example using this example after we do some other stuff. But for now, let's actually try to get some kind of definition for our matrix raised to a matrix. So let's actually consider two matrices, m and n. And we want to find out what exactly m raised to the n is. So in a previous video, I've defined the exponential matrix as well as the logarithm of a matrix. So it'd be nice if we can kind of combine those two to kind of deal with this thing right here. Because remember, if we have some number x and we want to express x in terms of base e, well, that's exactly e to the natural log of x. And we can do the exact same thing right here. We can look at this m right here and we can say, well, that's exactly e to the natural log of m. And all of that raised to the nth power. And this fact right here, you can prove it quite easily using the definitions I've set up in the previous videos. But this thing right here is true. Not sure about non-diagonalizable matrices. But if our m is diagonalizable, then this thing right here is true. And we're raising all of that to the power of n, or this matrix n right here. And whenever you have a power to a power, well, then you can just multiply the powers together. But here's our first problem right here. We can write this thing as e to the natural log of m times n, or we can just as easily write e to the n times the natural log of m. And that's a bit of a problem because matrices don't commute under multiplication. They're different things. M times n is not equal to n times m, for example. So we have to deal with this problem a little bit. And even though right here we have the natural log of m first and then the n, I'm not actually sure if the order is preserved in the exponent for matrices. That's something I'll probably have to look into or something. But we need to deal with this problem here somehow, because these two things right here, natural log of m times n, we kind of want it to be equal to n times the natural log of m in order to have some kinds of consistent result. Otherwise, we'll have like two solutions or something weird like that, and that wouldn't really be too great. So a nice way to go about that is just to simply say, well, why not just make the natural log of m times n be the same thing as taking n and multiplying it by the natural log of m. And while we may know a type of matrix that actually holds for these two conditions right here, namely symmetric matrices, I'm pretty sure there are other matrices that do have this property. But if we actually define m and n to be symmetrical, that means this condition here holds. And you may be asking, well, how about this natural log of m right here? Well, it really doesn't actually matter because the natural log of a symmetric matrix is actually still a symmetric matrix. And that has to deal with how you define the natural log of m, because if you decompose m into p dp inverse, well, p and p inverse kind of control whether or not the matrix is diagonal or not. So I have my CAS calculator with me right here, and I've actually defined a function for diagonalizing matrices. So let's see if I can find it. So diag matrix. And if we actually diagonalize a symmetric matrix, let's say 1, 1, I don't know, let's actually put in -1. It's -1 here. Let's actually make it match this matrix right here for now. If we do that, then we get this diagonalization right here. And if I actually change what the values of our diagonal matrix are on the main diagonal, let's change this 2 to a 5. Let's change this to, I don't know, 4, for example. Then notice the matrix we get out the end after we've multiplied all that together is still in fact a symmetric matrix. So I'm pretty sure the values inside of our diagonal matrix doesn't really matter because like the entries are already diagonal entry anyways. So I'm quite sure if m is a symmetric matrix, that means the natural log of m is also symmetric. And if you have that condition right there, that m and n are symmetric, that means we can actually define matrix to a matrix. And you see we actually have symmetric matrices in here, because in doing so we don't have to worry about this issue right here where natural log of m, where this exponent doesn't equal to this exponent or something weird. So with that out of the way, it doesn't matter which order of the natural log and the n we take, it's going to be the exact same thing anyways. So if we have it in this form right here, we can use what we know from taking the logarithm of a matrix to calculate the natural log of m. Then all we now have to do is multiply in by this n, and then take the exponential of that whole entire matrix. And that should give us the result that we want, which is m raised to the n, which is a matrix raised to a matrix. So with all of that out of the way, well, let's actually go ahead and calculate this example right here. So first of all, we want to turn this into base e a little bit. So this is equal to e to the natural log of this bottom matrix right here, so 0, 1, 1, 0, and all of that multiplied by 1, negative 1, negative 1, 1. Okay, so first of all, we need to calculate the natural log of this matrix right here. Let's actually call that matrix, I don't know, A, for example. So we want to calculate the natural log of A. And to do that, we need to diagonalize A first of all. So if we diagonalize A, we want to find the eigenvalues first. So to do that, we just take the determinant of the matrix lambda I minus A. And if we do that, that's the determinant of lambda I minus A. That's lambda minus 0, which is lambda. 0 minus 1 is negative 1, then negative 1 lambda, like so. And we want to solve for where this determinant is equal to 0. And while computing the determinant of this thing right here, we're just going to get lambda squared. BC, which is negative 1 times negative 1, which is exactly 1. So subtracting 1 from that, where that equals 0. And what that implies that lambda squared is equal to 1, which implies that lambda is equal to plus or minus 1. So those are our eigenvalues. And now to find our eigenvectors, well, first of all, we just need to find a null space of a specific matrix. So let's plug one of our eigenvalues into this matrix right here. So plugging 1 into here, we'll find the null space of 1, negative 1, negative 1, 1. And well, that's the exact same thing as the null space of, notice that if we take multiply this bottom row by negative 1, it's going to give us the exact same thing as the row on top. So we can kind of ignore that. So this can turn into 0, 0. And using the definition of the null space, that's exactly the matrix 1, negative 1, and 0, 0 times some vector xy, giving us the 0 vector. And if you think about this thing as a system of equations, you're going to get the equation x minus y is equal to 0. So x and then minus y right here is equal to 0 right here. So this implies that x is equal to y. So the vector xy we're looking for, so the vector xy is pretty much the exact same thing as xx, and that's exactly x times 1, 1, which is the span of 1, 1. So 1, 1 is a eigenvector that corresponds to the eigenvalue of positive 1. So let's actually put that down somewhere. So for lambda equals 1, we have the vector 1, 1. And also we have lambda equals negative 1, which we need to calculate the eigenvector of that now. So for lambda being equal to negative 1, well, instead of having the null space of this matrix, we have negative 1, negative 1, negative 1, negative 1. So just plug negative 1 into these lambdas right here. And well, if you do the same computations and everything, notice that negative 1 we can multiply by negative 1 to make 1. And this row is the exact same thing as the top row. So it just turns into 0. We don't need to worry about that. And well, if you kind of think about what we did before, turning this into kind of like a systems of equations, you're going to get the equation x plus y is equal to 0, which means that y is equal to negative x, which means that a vector xy we're looking for is the vector x negative x, which is the span of the vector 1, negative 1. So for lambda being equal to negative 1, an eigenvector that corresponds to that is the vector 1, negative 1. So we figured out our eigenvectors and our eigenvalues and everything. Now we can put it all into a matrix to express our matrix A as a diagonal matrix. So putting this all together, we have our P being equal to the matrix of eigenvectors. So we have 1, 1 first, and 1, negative 1. And our D matrix being the matrix of eigenvalues, and our eigenvalues are 1 and negative 1, so we'll just put it like that. So 1 first and then negative 1. And of course we still have to calculate our P inverse, and our P inverse, taking the determinant of this thing right here, is AD, which is negative 1, minus BC, which is negative 1, which is negative 2. So for our P inverse, what we have to do is change these two entries right here, so negative 1 and 1, and negate these two other entries, negative 1 and negative 1. And then we have to divide by the determinant, which is negative 2. So dividing this by negative 2 is just going to be a half. This is also going to be a half. This is also going to be a half, and this is going to turn into a negative a half, like so. So we have P, D, and P inverse. So that means our A, the matrix A, we're looking for is 1, 1, 1, negative 1, 1, 0, 0, negative 1, and 1 half, 1 half, 1 half, and negative a half, like so. Okay, so we have our A in a diagonalized form, and now we can finally take the natural log of A. And remember, if you watch my natural log video, if you want to take the natural log of A, if you have it diagonalized, then you just need to take the natural log of these two entries right here. So the natural log of 1, so if we want to take the natural log of A, natural log of 1, that's exactly 0. Natural log of negative 1, we need to go into the complex plane for now. So the natural log of negative 1, I've made a video on the natural log of negative numbers. That's actually going to be exactly I times pi. So natural log of A is going to be this whole junk right here. And let's actually multiply everything out right now, see what we get. So this is the exact same thing as 1, 1, 1, negative 1. Multiplying these two matrices together, we're going to get, well, first of all, we have a bunch of zeros right here. So right here, we're going to have a 0. And next entry should also get 0, because these two here are 0. And for this entry, we're going to get I times pi over 2. And then for this entry right here, negative I times pi over 2. And then multiplying these two matrices together, I think I can fit it right here. We're going to get I times pi over 2. And then for this one, we're going to get negative I times pi over 2. Then for this one, negative I times pi over 2. And for this one, I times pi over 2. And this thing right here is the natural log of A, and kind of like I mentioned before when we were trying to define it, A was a symmetric matrix, so this was our matrix A right here, and when we took the natural log of that, we still ended up with a symmetric matrix, so that was pretty nice. And now since we have a symmetric matrix times another symmetric matrix, which was up here, because this whole thing we've evaluated, which was this thing, we need to multiply it in by this matrix right now. So now this whole matrix to a matrix thing is going to be equal to E to this matrix up here, which is I pi over 2, negative I pi over 2, negative I pi over 2, I pi over 2, multiplied by 1, negative 1, negative 1, 1. And if you do that, you're going to get E raised to the matrix. Let's see, we're going to have I pi over 2 and then plus I pi over 2, so we're just going to have I pi. Then right here, we're going to get negative I pi actually. So negative I pi, down here is the same thing, negative I pi and I times pi. Okay, so this is our new expression for this thing right here. So E raised to this whole matrix right here. And now we have to diagonalize this whole thing again, and then we should be pretty much done. Alright, so now we need to calculate this thing right here. So let's call this matrix right here B. So we need to calculate E to the B somehow. So first, we need to diagonalize B. So we need to find the eigenvalues first, so taking the determinant of the matrix lambda I minus B. And that's exactly the determinant of lambda I, which is lambda minus I times pi. 0 minus negative I pi is just I pi itself. Then I pi down here, and lambda minus I times pi. Okay, and we want to solve for where that equals to 0. So taking the determinant AD is pi minus I, or pi minus I times pi squared, and then we want to subtract this whole thing squared, but notice I times I is -1, so we're going to add pi squared to this and solve where that equals to 0. So from here to solve for lambda, we're going to have to expand out this whole thing right here. So this is lambda squared minus 2I pi lambda, and then we have a plus I squared pi squared. But we have I squared right here, which is negative. So pretty much we have minus pi squared, then plus pi squared right here. We want to solve where that equals to 0. Negative pi squared and positive pi squared cancel it out. And then notice right here we can factor out a lambda. So we have a lambda minus 2I pi equals to 0. So that implies that lambda is equal to 0, or lambda is equal to 2I pi. So those are our eigen values. And now to find our eigenvectors, just like before, plugging those into this matrix right here and finding the null space of that. What we can actually do right here, since all of those will have a common factor of I times pi, we can divide it by I times pi to get -1, 1, 1, -1. And we can multiply the bottom, or we can actually add the bottom to the top to turn the bottom into 0. So we're going to have something like -1, 1, 0, 0. And if you think about this in terms of systems of equations, you're going to get -x plus y being equal to 0. That implies that x is equal to y, so vector xy we're looking for, that's our eigenvector, is the exact same thing as xx, which is the span of the vector 1, 1. So for our eigenvalue of 0, we have a corresponding vector, which is the vector 1, 1. And now to do the exact same thing for 2I pi, if we plug that into here, what's actually going to happen, we're going to get I pi for all of these entries. And since they have a common factor of I pi, we can divide everything through by I pi. And we're going to get 1, 1, 1, 1. And the bottom is the same as the top, so we can subtract the top from the bottom to get 0, 0 on the bottom. So it's pretty much going to be the exact same thing as this matrix right here, but we're just not going to have a negative right here. And if you think about that in terms of a systems of equations, just like before, that's going to be x plus y being equal to 0, which means y is equal to -x. So that means that vector xy we're looking for is x negative x, which is the span of the vector 1, -1. Okay, so an eigenvector corresponding to the eigenvalue of 2I pi is 1, -1. And now, since we have all of that information, we can put everything together in a nice diagonalized form. So B, our matrix, is equal to P, which is the matrix of eigenvectors, so 1, 1, 1, -1. And then our diagonal matrix, we're going to have a 0 first right here, because that's the one we did first. 0, 0, and 2I times pi. Then we have to calculate P inverse. But notice this matrix looks like the matrix before. So the determinant of this matrix is again going to be -1/2. And if we do the inverse for this matrix, we're swapping these two entries around. So this is going to be -1 and 1 here, and dividing by -2 because that's the determinant. We're going to get 1/2 and -1/2 right here. And negating these two entries right here and dividing by -1/2, we're going to get 1/2 and 1/2. And that's our B, okay? And if we want to calculate e raised to the b, then we just take e raised to the 0 and e raised to the 2I pi. And notice e raised to the 2I pi, that's exactly, well, 2 pi is a full revolution around, which just lands us at 1. So this thing right here is 1. E to the 0 is also 1. So this whole thing right here, that's actually the identity matrix, because we have 1, 0, 0, 1. And whatever we multiply that into, it's not going to change anything. So we can kind of forget about this matrix, just the identity matrix. And all really we're left with is this matrix times this matrix. And if you do the matrix multiplication on that, you're going to get, well, first of all, you're going to get 1/2 plus 1/2, which is 1, For the next entry, we're going to get a half minus a half, which is 0, and then 0, and then the last one is 1. So in fact, we actually end up with the identity matrix, which is pretty cool. So this whole thing right here just evaluates to the matrix 1, 0, 0, 1. And there you go. That's an example of how you raise a matrix to another matrix. So that is pretty much it, actually. Just remember that for the definition I used, we only have symmetric matrices here, and we only end up with another symmetric matrix. I'm not actually sure if you can do it with non-symmetric matrices. That's something other smarter people will have to look into, because I'm not actually sure if matrices can commute or anything in the exponent or anything. That's kind of beyond my level of knowledge. But that's how you could define how you would raise a matrix to the power of another matrix. Not something that has any specific geometric interpretation or anything. It's just some random math stuff that you can play around with. One interpretation, I've actually made a video on complex numbers as matrices. Maybe if you have a complex number z and a complex number w, if you raise z to the w and you write these two in terms of matrices, so you can actually write complex numbers as matrices. They have an equivalent relationship there. That's something you can use it for, but yeah, beyond that, I'm not sure if this has any real applications actually. So yeah, that's pretty much it for this video. I hope you guys enjoyed this one, and I'll see everyone next time.